Okay, so number one, it's asking for the maximum speed. So speed, let's think about velocity first, right? The highest velocity that we see is 3, because this is the velocity graph. And then also we see a velocity of -3 here. And you know that speed is the absolute value of velocity. So a velocity of 3 versus a velocity of -3, these are both going to produce a speed of 3 meters per second. So there's no other value that's more than 3 or less than -3. So it's a tie between velocity of 3 and velocity of -3 because they are both producing a positive 3 meters per second. We're talking about the absolute value. Okay. So 6D. Okay, so this is based off of the velocity sign line. We just want to figure out, how is the velocity, how is this particle moving, right? Because this particle is moving along the x-axis. So it's either going left, right, or it's going to be stopping. So first thing is we want to find the velocity function, which we did here. Set equal to 0, -1, -1 and 3. Normally I would put -1 onto my velocity sign line, but there is a restriction here in that t has to be more than 0. So I'm starting at 0 and I'm moving to the right. So -1 is out. So this is my starting point. And then 3 is also a place where velocity is, where the object is not moving. So now we have to figure out what is happening from 0 to 3 and then from 3 to infinity. So I'm using these test numbers. Any number between 0 and 3 will exhibit the same behavior for this particle. So I just chose 1. 1 seems like a convenient number. So 1 goes in for t. 1 minus 3 times 1 plus 2. That's negative times positive, which is negative. So that negative tells me that for 3 seconds, this particle is moving to the left. And if I plug in 4, 4 looks like a convenient number for me to test to the right of 3. Plug 4 in, positive, positive. That's positive. So that means from 3 to infinity, this object is moving to the right. So this kind of gives us a very helpful visual as to how the graph is moving, right? For 3 seconds, it's going left. Then it stops for a moment at 3 seconds. And after 3 seconds, it's going to turn around and move to the right. It doesn't have to always start at 0. It's just because my restriction starts at 0, so that's why I start at 0. Now, if this was not there and it said particle moves at all times for all real numbers, then I would not include 0 unless 0 shows up as a t value that I solve here. So if 0 wasn't in the restriction, I would include -1 and 3, and then that's it. And then for h, what's the total distance from 1 to 4 seconds? So we know that total distance is similar to displacement, but if there's a change in direction, we have to basically know where he changes direction so that we can count, right? Because otherwise, if he's going forward and backwards, we have to know where he changes direction so that we can make sure that we count every movement that he makes as a positive value. So if we're starting from 1 and we're going to 4, we just want to know, is there a change in direction between 1 and 4? And there is, because at 3 seconds, he's actually going to change direction. So now this 1 and 4 has nothing to do with the 1 and 4 that I have here. The 1 and 4 here is just for me to figure out what the signs are. I should just erase them after I figure out what the signs are. So I know that there's a change in direction at 3. So I need to also identify where he's located at 3 seconds. So that means I'm going to find his position at 1 second, position at 3 seconds, position at 4 seconds. Okay. And imagine yourself walking from this point to this point to this point, and you're just walking along these points on the number line. Hey, Raj. So for instance, let's say I start off at -9. And I walk all the way over on the number line to -25. And then I walk back to -18. So in 1 second, I'm here. 3 seconds, I'm here. By the 4th second, I'm here. Okay. And then so from -9 to -25, imagine yourself just walking, right? If you're walking, how many steps did you take from -9 to -25? And that's going to be 16 steps. And then from -25, you're going to walk back to -18. And that's 7 steps. And then 16 plus 7 is 23. So over the course of these 2 time intervals, the number of steps that you have taken is your total distance, 23. Okay, does that make sense?
Is that to me?
Oh, no, I was, Killian is online.
Oh, okay.
You have any questions?
Yeah, can we go over like a surface area for sphere question?
Mm-hmm.
Like, what does the formula look like for that too? Because like I know the volume is different.
Yeah, I'll give you those formulas.
Okay.
But let's see.
The main idea is just like take like the derivative of all the things and then
Yeah.
whatever's left, like whatever's not filled in, that's what you solve for.
Usually, right, usually. But we can pick one out too. Morning. It's in the back. Do you need a scratch sheet? Okay, and do you need a calculator?
Yes.
Okay. You grab that. Okay, I'll go over the one that we did in class. Just, I mean, they're all going to feel the same. So this is example 3 on page 13. Morning. Okay, a spherical balloon is being inflated at a rate of 10 cubic centimeters per second. Find the rate of change of the surface area of the balloon at the moment when the surface area is 64 pi. So I'll give these formulas to you if these problems show up. Volume is 4/3 pi r cubed, and surface area is 4 pi r squared. Okay, I like to go ahead and find the derivative, get all that out of the way, and that way I have everything in front of me for me to plug in. So remember, pi is just a number, so 4/3 pi is just some number hanging out here. V becomes dv dt, r cubed becomes 3r squared dr dt. Okay. Surface area, S becomes ds dt, 4 pi is just a coefficient that stays, r squared becomes 2r dr dt. Okay, good so far. Okay. So now I'm going to clean both of these equations up. Get the 3's to cancel out here. Clean this up here. So now I have everything in front of me. I have my volume, my surface area, my dV/dt, my ds/dt. Everything that I need to solve is going to be coming from one of these equations or a combination of them.
Why do you need the volume and the surface area if it's only asking for find the rate of change of the surface area?
Well, it depends on the information given to me, but I know that if they give me something related, I know I can use this to plug in and find. I don't have to use all of them, but at least these equations are at my disposal.
Also, like you can find dr/dt, for example.
Yeah, so I'm going to just gather information and see, okay, what do I need and how can I use these tools to help me get to my endpoint? So this is what I can gather, right? dV/dt is 10 because we know that the balloon is being inflated at a rate of 10 cubic centimeters per second. Find the rate of change of the surface area. So I'm looking for ds/dt at the moment when the surface area is 64 pi. So S is 64 pi. So we know that if we want to solve for ds/dt, we need to find R and dr/dt. But they don't give us R and dr/dt. They gave us dV/dt and S. So we have to figure out, okay, how can I use this information to eventually get to what I need? So this is where this puzzle comes in. So how can we see a pathway where we can get to R and dr/dt given this information?
You can plug in dV/dt.
Right, but the thing is, if I plug in 10 in for dV/dt, I'm still stuck not knowing what R is. So
could you plug back to the original function?
which one?
Like v equals 4/3 pi r.
Okay, so what would you do here? What would you plug in?
Right, you can't do that.
Right, so we're kind of stuck, right? At least with this, at least for the moment, right? I mean, this is a good strategy once we find R, but we're kind of at a dead end if we're starting here. Okay, what else do we have that we can use?
S equals 64.
Okay, so how can we use this?
We can plug into S equals 4 pi r squared.
And then the goal here, we can do what with that?
We can find R.
Find R. And once we have R, then that clears up our ability to make progress here. Okay, so 64 pi will go in here. We can solve for R. So replace S with 64 pi. I can divide the 4 pi over. Pi cancels out. 64 divided by 4 is 16. 16 equals R squared. Take the square root. R equals 4. So that's the first piece that I need, right? And that will help me here. And it'll also help me make some progress on this end. Okay, so I have R, which is good, but I still need dr/dt. And this is where dV/dt can help us out, right?
You use the bottom left.
Right, we can plug that 10 here, plug 4 in here, and now we have a pathway towards solving for dr/dt. Okay, so we plug 10 in to the dV/dt equation. So 10 equals 4 pi r squared dr/dt. We just found R is 4, so we put that in to our dV/dt equation as well. So now the only variable left is solve for dr/dt. Divide this to the left. This is 64 pi, so 10 over 64 pi can reduce to be 5 over 32 pi. So these are the two things that we need for my ds/dt, which is ultimately the variable I'm looking for. So 8 pi times 4 times 5 over 32 pi. Clean all that up. I get 5 centimeters squared per second. Now, this cleans up nicely, but we got to make sure we know how to do the units of measure. S is surface area. Think about that word area. That's a two-dimensional unit. So centimeters squared. Time is seconds. So centimeters squared per second.
And then you were mentioning how a cylinder is easier to solve than a cone, and why is that?
Because with cylinders, you know how cones, we kind of have to go through the similar triangle because R is changing and H is changing. So we have to hold on to both variables and we have to replace one in terms of the other. But with cones, Sorry, with cylinders, your radius never changes. If your radius never changes, there's no need to hold on to a variable. We can just replace that r with a number, and that makes the equation a lot easier because we just got rid of the variable without having to do much work. And then once it's down to one variable, then on both sides, then you just go through your derivative and plug in. So we don't do similar triangles for cylinders, even though the formula looks all very similar to cones.
And the formula for cone, cylinder, and sphere given, right?
Yeah, I'll give those to you. Yeah.
Okay. Could we also go over a shadow problem?
Mhm. So this is on page 21. This is one of the day 2 problems here. This is a homework problem. Okay, a child is walking directly under a street lamp that is 6 meters above ground. So I'm going to always set it up this way here. If the child walks away from the light at a rate of 20 meters per minute, how fast is the child's shadow lengthening? So just to remind us here, dx dt is the rate of change of the person walking. dy dt is the rate of change of the shadow lengthening or changing. And if I add the two rates together, that's going to be the rate of change of the tip of the shadow in relation to the ground.
Wise, the tip of the shadow.
So if the person is walking and the length of the shadow is changing, then the tip of the shadow is going to be moving at a pretty fast rate. Right? That tip of the shadow is going to move along the ground based off of how fast x and y are both changing.
Okay.
So if I add the two rates together, that's the tip of the shadow. Okay, we can set up our proportions here. We can say the small height, the height of the small triangle is to the height of the large triangle as the base of the small triangle is to the base of the large triangle.
We just as a cross multiply.
And then cross multiplying, we can just get this cleaned up so that we can find the derivative. Okay, an easy equation for us to find the derivative. X becomes 1 dx dt. And then 5y becomes 5 dy dt. Okay, so the child is walking away from the lamp. So we know x is increasing. He's walking away from the lamp is also positive. So we know dx dt is a positive 20. So if I want to find dy dt, I can just use this equation, right? Divide both sides by 5, I get 4. So I know that the child's shadow is lengthening at a rate of 4 meters per minute, sorry. It's not asking for the tip of the shadow, but if I wanted to find the rate of change of the tip of the shadow, it'll be 20 plus 4, which is 24 meters per minute. I'll call this part A, and this is part B, even though it's not asking for part B.
All right, thank you.
Okay, so Okay, so this is on page 13 again, back to the cone problem. Okay, so we have a cone opening down. Anytime you see a cone problem, you know you have to work a proportion equation to get one variable in terms of the other. So here I can say R over 5 is equal to H over 12, because the radius of the small cone is to the radius of the large cone as the height of the small cone is to the height of the large cone. Cross multiply, and I'm going to gather some information here. dV dt is 10 because water is flowing into the tank. Find the rate of change of the depth of the water. I'm looking for dH dt when the water is 8 feet deep. And we don't want to use this until the end because this is just a moment in time that we can use once we have our derivative set. So this is really the hint here. I'm looking for dH dt, so dH dt will show up more easily if my equation has an h in it. If it's left with an h, then the derivative will just produce dH dt. And so that, because I'm looking for dH dt, that helps, that at least that kind of guides me to think, well, if I can get the r to be in terms of h, then if r is out of the way, then the h will just naturally produce dH dt. Right. So once I cross multiply and solve for r, I get r equals 5h over 12. Now I can put this in for my r. Okay, so my goal initially is just to get my equation cleaned up to the variable that I prefer. Okay, so r gets replaced with 5h over 12. I'm going to clean all this up, multiply this through. I don't want to have to go through product and chain when the only thing I need is power rule after I clean up. So distribute the 2 through, I get 5 squared, h squared, 12 squared. Okay, continue cleaning up. All the coefficients can go together. The h's can merge together as well. So I get 25 pi over 432 h cubed. Okay. So now we can find the derivative. V becomes dv dt. Coefficient is just some number that's going to stay. H cubed becomes 3h squared dH dt. Okay. So the hard part is getting to this point. Once you're here, you're just plugging information in. dV dt is 10, h is 8, and then you're just dividing, multiplying, dividing, and trying to solve for dH dt.
This year.
Mhm.
For one of the approximation questions, you just have to put it in a tangent line equation, and then if it's this way, it's underestimating, right? And this way is
Overestimating, yeah.
right. And then L'Hopital is also on the quiz, right? Okay.
Always check to make sure it's 0 over 0 before you do anything L'Hopital related.
When it's like infinity over infinity, it's like
I would say infinity over infinity, we have better, more efficient rules for it. But the nice thing with L'Hopitals is if you for some reason forget those rules, L'Hopitals can still help catch you.
Yeah.
So normally I would say compare degrees with infinity, or to comparative growth rates. But if for some reason forget those rules, then L'Hopitals will still get you to your answer.
when you want to find the total distance, you just you just set the equation to 0, like whatever you have.
Velocity equal to 0, yeah.
Yeah, you set the velocity equal to 0, and then that'll tell you what points it turns, right? And then you just solve for each of them and then find the distance.
But then don't add the numbers, right? You're putting those numbers onto a number line and you're walking between those and counting your steps. So, yeah. Okay.
How do you find when the particle changes directions?
You set velocity equal to 0. And and then you use test points on either side of that. That t equals, let's say, yeah, I'll show you here. So you set velocity equal to 0. Find your critical points. Now, -1 is not on my radar because it's at the top of the page. It's only when t is greater than equal to 0, so -1 is out. So I'm going from 0 to infinity. 3 is a place where my velocity is, this object is unchanging. So now I want to 1 and 4 because these are convenient numbers. If I plug 1 into the velocity function, I get the negative values. So that tells me that for the first 3 seconds, it's moving left. And if I plug 4 into the velocity, I get positive. It's moving right here. So if you see a change in sign at a place where the object is not moving, that means it's changing direction because it's moving left, he's stopping, moving right. So that tells me there's a change in direction.
Okay.
Thank you. Yeah, let me know if you have any questions you want me to do.
What formulas do we actually know?
Yeah, so I have those listed at the bottom of page 4. So Pythagorean theorem, area and circumference of a circle. So that's area is pi r squared. Circumference is 2 pi r. Area is x squared. Area of a triangle is 1/2 x. And then SOHCAHTOA as well.
Can you do that has number 9 on 4.3 AP practice and ask
No, which page is that?
26.
Okay, I'll go over that. Okay, the whole thing or just parts of it?
It's mostly on how to like start it because then the other parts usually fall into it. But
Yeah, so first thing we do is we draw our right triangle.
I have a question about
Yeah.
that. Is there more than one way to draw that? Like,
There is, yeah.
So
I mean, you can, if you draw it another way, it'll still work. Draw it this way.
I'm drawing it that way.
Oh, okay, yeah.
I'm gonna check the key and that's the other way. So I can.
Yeah, I purposely drew it this way because I want to make sure that students don't associate direction with the sign of the rate of change. Because here, x is increasing, so dx/dt should be positive. But sometimes students see that left, they feel like they gotta go left is negative. They think left is always negative and think down is always negative as well, which is not true. So that's why I purposely drew it that way instead of this way. But Okay, so Pythagorean theorem, x squared plus y squared equals z squared. We find our derivative. All of our d over dt shows up. We gather all the information that we can from the problem. Plug it in, and then solve for dy dt, -12. Any questions with part A? Now, part B, area of a triangle is 1/2 x times y. So we have to go through product rule, f prime g plus f g prime. Use everything from part A to fill in the missing pieces, and then rate of change, area and time. Area is square meters, time is seconds, so square meters per second.
Since none of the numbers on the triangle are constant, you can't like avoid product rule.
Can't avoid product rule, right? Some triangles you can, depending on what the motion of the problem is, right? So if you can imagine the motion of the problem and one side never changes, then you can avoid product rule. Okay. Part C, find the angle when the top of the ladder formed by the ladder and the ground. So my theta is over here in that corner. I would prefer to avoid quotient rule, and here I'm just hunting for something that is a constant. So if I can involve the hypotenuse, I can just avoid quotient rule. So if I have sine of theta equals y over 13, that's perfect. I can just pull that 13 out as 1/13 y, and I can just do power rule rather than going through quotient rule. You can still go through quotient rule, it just feels messier, but it's fine. And then we just find the derivative, cosine theta d theta dt, 1/13 dy dt. And then I like to draw a second triangle to help me figure out what I can replace with cosine theta. So I'm going to redraw this triangle, but I'm going to fill in as much of the information for that moment in time. So I know this is a moment in time when 5 and 12 and 13, all these, well, actually, these are all sides that we found from part A, right? So cosine theta is adjacent over hypotenuse. We put that in for cosine theta, and then everything else we can just gather from part A, and then we solve for d theta dt, -1, and our theta is always radians, so radians per time unit. Mhm.
One last thing, not about this. For the justification of like overestimate or underestimate, can we just say it's concave?
Yeah, that's all you need, yeah. Mhm.
T equals E. you do number 13 on page 19? Not number 13, number 23. Because there's no one.
Okay.
Get rid of one.
Okay, so the thing to know about cones is that we know we have to replace one of the variables. There's too many variables for us to define the derivative. Or if we build out the derivative with product rule, we're gonna have too many variables, not enough information. So the first thing we can do is create a proportion equation. We know the radius and the height of the cone shaped by the water is always changing. So R is to 4 as H is to 16, cross multiply. And I decided to solve for R because I want to replace R. The reason that I want to replace R is because I'm looking for dHdt. If I want to find dHdt, I would prefer to have H in my equation because H will naturally produce dHdt easier for us. So we cross multiply, we solve for R. R is H over 4. Replace H over 4 in for R. Clean all this up, okay? And the thing that I see some students do is they try to just jump through the derivative too soon, right? There's no need to do any fancy derivative rules. All we need is power rule, and we do need to do some cleanup. So distribute the 2 through, multiply all the coefficients together, merge all the H's together. Now this is clean, right? All we need is power rule here. So B becomes ddt. Coefficient stays, H cubed becomes 3H squared, dHdt. And then that's the hard part. The hard part is getting to this point. After that, you're just putting information in and solving for the missing variable that you're looking for.
There's calculators on this, correct?
You can just calculate it out.
There's no way to check a related rate on a calculator, right? There's no way to check a related rate on a calculator.
Not in terms of plugging in and finding the answer. Just be aware, sometimes pi is supposed to be in the denominator, so if it's in the denominator, don't just let it go to the top, that's different, right? So if it ends up in the denominator, then just leave it in the denominator.
Are we focusing too much on related rates? Like, is this not like a main portion? Because there's 4 sections to the quiz.
It is, this is the main portion. Okay. They're gonna have 3 related rates. And then the L'Hopital's and linear approximation are very minor. And then you have that one particle motion problem.
So it'll be like a page apart.
Yeah, page
couple L'Hopital's and then a couple of the.
Yeah, a couple, 2 L'Hopital's, 1 linear approximation, and then 3.
I'm assuming it's like, just like, so is it like 3 or 4 pages?
Yeah.
Okay. These are big. All right.
Yeah, this is the big, yeah.
And we get you close on the key, keep it reduced. So we get one of the sphere or cylinders, and then one of the cone or similar right triangles, and one of the triangle ones, or the other triangle one.
Yeah, so you'll see a problem like this. This is page 4 with the 3 parts there. Okay, so you'll see one of those. But yeah, you'll have one similar triangle problem, either a cone or the shadow problem. And then you'll get a cylinder or a sphere problem. So that's 1, 2, this is 3.
And the shadow ones, it's like you find dy dx.
UIDT.
Dy dt.
Yeah, so I did one earlier. I'll just show. This is page 21 here. Yeah, so dx dt is your rate of change of the person walking. Dy dt is the rate of change of the shadow lengthening. Then 2 rates added together is the rate of change of the tip.
Too bad.
Yeah.
Will we get our tests back?
Yeah, I'm working on it. I more than halfway through. Hopefully tomorrow I'll do this year grades.
Thank you.
Yeah, as soon as you guys walk in, I'll have the test laid out so you can start working as soon as you can.
And homework's due tomorrow, correct?
Homework's due tomorrow. I'll send out a reminder though.
You want to see my 5.1?
Just show me tomorrow. Yeah. Thanks, guys. See you guys in class. Bye.
Thank you.